This session highlights Fire Safety Research Institute FSRI research on chemical exposure risks faced by firefighters during vehicle fires, including those involving electrical vehicles and lithium-ion batteries. The presentation examines differences in smoke composition between electric and internal combustion engine fires and evaluates fireground exposures during suppression activities. Findings will inform tactical considerations to help reduce occupational health risks during and after emergency response operations. The speaker for this session is Dr. Chandler Probert, who is a research engineer with the Fire Safety Research Institute, FSRI, part of UL Research Institutes. He holds advanced degrees in polymer and fiber science from North Carolina State University and leads research on firefighter PPE contamination, including exposures from electric vehicle fires and structural burns. His work focuses on understanding and reducing chemical exposures on the fire ground to help mitigate long-term health risks, including cancer among firefighters.
Hello, everyone. I'm Dr. Chandler Probert. I'm a research engineer with FSRI, Fire Safety Research Institute. And today I'll be speaking about electric vehicle firefighting, health hazards, and PPE contamination. And again, I would like to say thank you for inviting me to speak at the CFSI Virtual Symposium. So I'll just jump right in. So we have a very interesting project focused on electric vehicles, and this project came to be mainly due to the potential risks of these electric vehicle fires. And we can see just from looking at the vehicles on the road that electric vehicles are becoming more and more prevalent. Data collected by EV FireSafe, an Australian organization, has shown that EV market share has steadily been increasing since 2018, 2019, which is about that inflection point. And we can see that with EVs becoming a larger portion of the automotive market, there is a direct correlation with the number of electric vehicle fires. And the most common causes of these electric vehicle fires include collisions, equipment malfunction, and then smaller scenarios such as submersion, external fires, arson, even fires starting from repairs, overheating, and then other miscellaneous causes. So with these electric vehicle fires being more hazardous, this causes greater risk for firefighters in relation to the exposures to the battery gases and combustion products, and as well as the exposures and contamination to their PPE equipment. These exposures can either be acute or chronic. Both of these exposures can have separate risks. For the acute, this can include respiratory health risks, as well as dermal and skin health risks, such as blisters and lesions, skin irritation. And all of this is resulting in firefighters having a greater risk of being injured on the job, which in rare cases results in hospitalization, decreased work capacity, and in some cases, extended time off from the job, cases lasting up to months at a time. So this talk is going to be focusing on the results from different electric vehicle fires that our project was able to conduct and characterize both air and PPE contamination from these types of fires. So there are several different chemicals that we are interested in, ranging in toxicity from possible carcinogens to probable carcinogens, also including known carcinogens. And these chemicals include PAHs, also known as polycyclic aromatic hydrocarbons, VOCs, volatile organic compounds, and other chemical compounds that are at greater risk for electric vehicle fires, such as metals, acid acids, inhalable particulates, and fluoride compounds. So, a firefighter can be exposed to all of these compounds simultaneously. And again, like I previously mentioned, in both acute and chronic exposures. Acute is more of the immediate exposures, and a chronic exposure would be if firefighters are responding to electric vehicle fires frequently or even infrequently over the course of their career. What are these exposures going to impact their health after their career as a firefighter? So we have several different full-scale fire tests separated into two batches, the free burn experiments, and we also have data which we are now analyzing for suppression and fire control experiments. Today I'll be focusing primarily on the free burn experiments, and then I'll be going over the characterization, um, again for the air, breathing zone, and PPE swatches. And this is just a smaller part of an overall larger study where we also have measurements of fire behavior of these different types of fires. And like I mentioned, the effectiveness of different fire control techniques. Okay. So the overall experiment setup, we had electric vehicles and internal combustion engine vehicles. For the free burn experiments, the EVs were placed in the middle of a test pan at 100% state of charge. And for the internal combustion engine vehicle counterparts, they were filled with a full tank of gasoline. Around the vehicles, we had different sampling locations. We also had imaging cameras, both infrared and FLIR imaging cameras. We had PPE stands, which is shown in the bottom right. You can kind of see the cement board. This is where we had our PPE samples as well as air sampling pumps. And then we also had passive air sampling with silicone wristbands. And then the sampling locations for the PPE stands were placed at 10 and 15 feet off of the hood and trunk of the vehicle, respectively. And then lastly, we also had a plume sampling container, which is this gray box up at the top of the image. Again, we had the PPE swatches and air sampling and also wristband samples at this location as well. And in order to begin the fires, we placed a propane burner underneath the vehicle to initiate thermal runaway. And the fire was monitored until the fire reached thermal runaway. And once that was identified, we allowed the fire to propagate for 6 minutes before suppression began. The 6 minutes was intended to simulate a fire engine response. So we tested 9 vehicles in total for the free burn experiments, 6 different EVs and 3 different internal combustion engine vehicles. For the EVs, they cover a range of what would be commonplace to see on the road today. And the electric vehicles also had a range of different battery pack sizes, ranging from 28 kilowatt hours for EV3 up to 91 kilowatt hours for EV5. And I'd also like to point out that the battery packs of the larger SUV and truck EV vehicles can reach up to 200 kilowatt hours. So, whatever contamination we see from these experiments can be even greater in those larger vehicles with larger battery packs. So, with that, I'll jump right into the results. So beginning with the inhalable particulates, this is defined as anything less than 100 micrometers. And here we have a figure showing the concentrations of the inhalable particulates in milligram per meter cubed. We can see that at the 10 and 15-foot floor sampling locations, we can see that the concentrations of these inhalable particulates is generally less than the plume sampling location. And we can also see that the concentrations between EV and ICV are similar for inhalable particulates. And then this is the differences between the floor and plume concentrations is to be expected, with the plume being the higher concentration of smoke and particulates as well. Now, for PAHs, again, we can see the same general trends as the inhalable particulates. The 10 and 15-foot distances aren't very dissimilar, and then the concentrations are similar between EV and ICV for the floor locations and even in the plume, but the concentrations in the plume generally being higher for the plume. Another thing to note is that the concentrations of pHs at the floor locations, which is where firefighters are most likely going to be operating when they encounter an electric vehicle fire, these concentrations are similar to the exterior of training and structure fires. Now, for metals. Metals are obviously a large concern with the electric vehicle fires, primarily due to the lithium-ion batteries, which are present in the battery packs of these vehicles. And we can see that the battery metals shown here, nickel, cobalt, manganese, and lithium, are in greater concentrations in the electric vehicle fires than they are in the internal combustion engine fires, which makes sense. We wouldn't expect to see these battery metals in the ICV fires since they shouldn't be in the vehicles to begin with. And that's exactly what we see here. And then the other thing to note is that nickel is significantly higher than the other battery metals. And we can see that cobalt and manganese are generally in the similar proportions. And this all makes sense with the battery composition of the lithium-ion batteries in these vehicles is generally 60% nickel, 20% cobalt, and 20% manganese. And these ratios is roughly the ratios we see in these concentrations. So overall, we can see that there are high concentrations of battery metals in the plume during these EV fires. And then another thing to note is that while nickel is generally elevated, the other battery components are within 0 to 10 milligrams per meter cubed. We also examined concentrations of other metals, which would be more likely in the internal combustion engine vehicles, such as copper, lead, aluminum, and antimony. And again, we can see since these metals will also be present in ICV vehicles, that they are in more similar concentrations, with aluminum being elevated in the EVs, as well as antimony being elevated in EVs as well. And then bottom right, it should be noted that chromium and cadmium were below the detection limits, and arsenic was identified in 2 of the EV plume samples. And another thing these metals, although present, they're in much lower concentrations compared to the battery metals. Um, and that's again due to the prevalence of the battery metals in the lithium-ion batteries of the battery packs for electric vehicles. So for acid gases, we looked at HCN, HCl, and HF. Similar to pHs and inhalable particulates, there are similar concentrations between EVs and ICVs. And one notable concern with EVs is HF, and we looked at HF both in its both as hydrogen fluoride and fluoride ions separately. So in this graph, we can see that fluoride ions are generally higher than pure HF in the EVs. And generally, there is no HF or fluoride ions in the internal combustion engine vehicle fires. However, in the plume, we can see that there's a little bit in ICVs for the fluoride ions and HF, but generally, the largest concern is the plume fluoride ions for the EV vehicles, as well as HF for the EV vehicles. So overall, the fluoride particulates are greater than just HF, and they're more likely to be present in EV fires. So for the PPE swatch results, this graph shows the metal contamination on the outer shell floor samples at the 10 and 15 feet locations. In all of the previous graphs, it again showed that there weren't very large differences between the two distances. So in this graph, all of those samples are combined and just shown as general floor sample locations. And similar to the air sampling, we can see that, again, nickel is generally higher than the other battery metals, manganese and cobalt. And then their internal combustion engine and counterparts are significantly lower at or near zero for these metals. Continuing on to the other non-battery metals, pardon me, aluminum and copper, we can see that there is more similarity between the internal combustion engine vehicles and the EV vehicles. And then it's also interesting to note that lithium was much lower concentrations compared to the other battery metals for the PPE contamination, as it was more similar in the air contamination to the other battery metals. And then lastly, chromium, arsenic, and lead. Um, these metals were all present in most of the EVs and internal combustion engine vehicle fires. However, they are at much lower concentrations. Now, for the plume samples, we can clearly see that the scale of this graph is significantly higher. So again, nickel is largely present, followed by a large presence of manganese and cobalt. And I'd also like to note that the results from ICV1 plume samples were excluded from this data set because during that experiment, the PPE swatch actually fell from the sampling container and fell onto the floor. So we had to throw those samples out because they were contaminated from the floor rather than just the fire itself. Moving on to the other metals. So again, aluminum and copper were present, and lithium was more similar to these metal concentrations than they were to the other battery metals. And as we continue to chromium, arsenic, and lead, we can see that the concentration of these metals is generally decreasing, again, showing that the concentration of these metals is generally lower than all of the other metals. And for lead, we can see that the ICV 2 and 3 are slightly higher than the lead concentrations in all of the EV samples for the outer shell and the plume. So what about the other layers of PPE, the moisture barrier and thermal liner? So for the floor, which is the left half of this graph, we can see that most of the metal contamination is present on the outer shell, while there is some contamination on the moisture barrier and thermal liner. And between the moisture barrier and thermal liner, there is slightly more contamination on the thermal liner. And for the plume sampling location, most of the contamination is present on the outer shell, while there is less contamination on the moisture barrier and thermal liner layers. And the greater contamination on the thermal liner for the floor sampling locations might be due to the way we sampled the PPE swatches using the cement board. There was some small indentations and grooves providing a texture. So those smaller groove areas may have provided an opportunity for the smoke to navigate around the backside of the PPE swatch, contaminating the thermal liner. Now for pHs. Now this is a larger image, so I'll break it down briefly. So this is the 16 pHs, and moving from left to right increases in molecular weight. So starting with naphthalene, which is the smallest of these compounds, all the way up to benzo-GHI parylene, which is the largest of all these compounds. And then it is separated into the three layers, the first grouping being the outer shell, and then the middle is the moisture barrier, and then the bottom third is the thermal liner. Each of these is then separated based on the vehicle experiment. And then all of this data points are highlighted based on their percent, based on their relative presence. So for all of the samples, EV1 through EV6 and EV1 or ICV 1, 2, and 3, the darker the red, the more present the pH was. So we can see that in EV6, there was high concentrations of phenanthrene, and for EV1, there was high concentration of dibenzo-AH anthracene. And then this kind of color coding is applied to each layer of the PPE swatch. And then we also have the total pH. And then again, the heat map color coding is applied strictly to this one column. So the darker the red, the more pH contamination. And we can see a general trend of the outer shell for the EVs is generally the most contaminated, while the moisture barrier is a yellow to orange, and the thermal liner is yellow to green, showing that most of the contamination is present on the outer shell for the floor samples. And we can also see that there's a general trend for the larger molecular weight pHs to be present on the outer shell, and there is a less likelihood of the larger molecular weight pHs to be present on the moisture barrier or even the thermal liner at the floor location. So again, this is the same heat map for the plume sampling location. And this is slightly different than the floor location, where we can see there is a general greater concentration of the medium molecular weight pHs, ranging from phenanthrene, fluoranthene to pyrene. These are generally darker and have greater concentration relative to the other pHs in the plume than we saw in the floor sampling locations. Again, we can see that most of the contamination is on the outer shell, and with contamination decreasing from the outer shell to the moisture barrier to the thermal liner. And then again, the trend for the outer shell to contain most of the pHs, small, medium, and high molecular weight pHs, is clearly shown with this general trend as the closer to the thermal liner you get, the more likely it is it's going to be contaminated with these smaller pHs. So the general takeaway from these results is that the VOCs, pHs, and inhalable particulates have similar concentrations between EV and ICV fires, and these concentrations align with the exterior of structural and training fires. In EV fires, there were high levels of nickel, manganese, cobalt, and lithium metals. Similar to the VOCs, pHs, and inhalable particulates, acid gases were similar between EVs and ICVs. Fluoride particulates were elevated in EV fires compared to HF. Generally, plume contamination was an order of magnitude greater than the floor samples for PPE. And low molecular weight pHs dominated the contamination profile and frequently penetrated beyond the outer shell to the moisture barrier and thermal liner layers. So we are currently publishing all of our results. We've gone through most of the full-scale burnout experiments, which I covered. There is, again, also the heat transfer and fire dynamics results. And we are currently working on publishing both the air sampling and PPE swatch samples data and results from the suppression experiments. So you can find our information in research journals such as Fire Safety Journal, as well as the raw results and data in brief. Or if you'd like to visit our website, you can feel free to scan the QR code. We have a lot of useful training exercises and videos for anyone to follow along. And then if you have any more specific questions, feel free to reach out to me at my email. And also feel free to reach out to Richard Kessler. He was one who was responsible for all the air samples. And then I also like to acknowledge Adam Bowery, and then also our research partners, Duke University, UL Solutions, as well as NIOSH. We have a great team. We couldn't have done it without everyone who was able to pitch in and help out. So if you have any questions, feel free to contact us or check out our website. And with that, I think I'll have a minute or two to give back. And again, thank you all for having me.
On behalf of the Congressional Fire Services Institute, thank you to everyone who joined us for today's virtual mini-symposium series, What's Next? We especially want to thank our presenters for sharing their expertise, research, and insight on these important issues impacting firefighter health, safety, and wellness. Today's discussions highlighted both the challenges facing the fire and emergency services community and the innovative work being done to better support firefighters through research, collaboration, leadership, and education. From mental wellness and occupational cancer screening to emerging hazards related to electric vehicle firefighting, these conversations are critical to advancing the health and safety of those who serve their communities every day. We appreciate your participation and engagement throughout today's mini symposium and encourage you to continue these important conversations within your departments and organizations. Thank you again to our sponsors, the First Responder Center for Excellence and UL Research Institute's Fire Safety Research Institute, for sponsoring today's mini symposium. And thank you all for joining us. We look forward to connecting with you at future CFSI programs and events.